In this video, I'm going to talk about random effect model using mixed effect model. And there are three types of random effect model mainly, and random intercept model, and random slopes, and random intercept and slopes. So we are going to talk about a concept of each model. And before we talk about specific about random effect, and let's review a concept of repeated measures analysis. And today's example is dental growth data among 10 girls and measured at age 8 and 10 and 12 and 14. Okay, so each line indicate a single girl. So this is for measurement from a girl, and this is for measurement from another girl. So there are 10 girls altogether. Now we use SPSS data set called growth.long.sav. This is the longitudinal data format. So let's go ahead to conduct the linear regression. And I know it's wrong to do linear regression, but I like to see what happens if you mistakenly conduct linear regression. So data set we have is this. And again, we are only assessing effective age on dental growth measures among 10 girls. So we are going to unselect boys measurements. And so if you go ahead to do linear regression, so let's use general linear model option for linear regression, and you'd include you put the growth as a dependent variable and age as a covariate. So that today's example, instead of comparing mean of growth at a different age category, and we will compare slope of age. Okay, so SPSS consider age as continuous variable, and we put the age under model and continue, and let's click OK. And this is a result of this model. So what the model did is, if we show the data with the graphs, let's do scatter plots. Put the scatter plot in growth as y, age as x. Okay, so this is what this model did. So put the straight line over age and then assess whether the slope is positive or negative. And we know we can't really use linear regression because linear regression have assumption and say all observations have to be independent. And a quick way to check this assumption, go to your working data set, and if the data set contain more than one line coming from a single patient, you are violating this assumption. So as you see, there are 4 lines from each patient in this data, so it's clearly we violated assumption. So we cannot use linear regression for this data. But if you look at the outcome, and you can interpret this beta coefficient as average annual increase in dental growth measure, and that is 0.49 millimeter, and which is statistically significant. But we know this p-value is wrong because probability computation is based on all the observations are independent. So why it's wrong to use linear regression? What's wrong if data are not independent? And this is an example we saw in the previous video. So these black dots indicate data for CRP from a single patient, and these red dots indicate data from another single patient. Okay, so these two, there are 2 patients. One have a higher CRP value, and one has a lower CRP value. And then both patients, when they use catheter, and CRP level increased. Okay, so when you use linear regression, a model assumes all observations are independent. Therefore, it considers these observations are coming from different patients these observations are coming from different patients. So it assumes these observations should be as different as data from two different people. So that's clearly biased p-value calculation. As you see, data from a single patient is a lot more similar than the data between two different patients. Okay, so in order to, one way to tell SPSS, and these are from same patient, and we somehow have to model between patient variation. Okay, and so we tell there are difference between this person and that person. Okay, and then by removing between patient variation, in fact, and we can focus within patient variation. So when you consider whether catheter has impact on CRP, you don't really compare this observation to this observation, right? So those observations are from two different patients, right? So you don't compare this observation to that observation. That has no relevance, right? So when you want to see effect of catheter, and I'm sure you will compare this observation to the rest of this person's observation, right? So those have nothing to do with data from this person, right? So using random effect, so the goal, one of the goals in today's lecture is I want you to think how we can introduce difference between patient, and so that we can remove between patient variation, then analysis can focus what happened within patient. The simplest way to express between patient variation, I call the word individuality among patient, maybe to fit separate regression line for each child. And we can easily do this by including ID in a linear regression. Okay? And so you plot. This will give you different intercepts and slopes for each child. And however, this approach will cause severe overfitting in your analysis because you have too many parameters to estimate. And of course, we are not interested in assessing different effect of age for each child. So what I mean by is we could have performed linear regression, and which consider ID as another grouping category. So you could include ID as a fixed factor. It's a categorical variable. Okay, and then you put age and ID under the main effect, and with the interaction between age and ID. And by doing this, okay, and you fit the humongous model. Okay, and you have all the parameters for indicating different intercept for different patient, and also different slopes for different patient. And quick eyeballing. Okay, so by looking at this, you know ID number 11 person is reference category, and because we did not change the reference category, and SPSS use the largest number as a reference category as a default. Okay, and so this intercept is intercept for ID number 11 person, and this beta coefficient for age is slope for ID number 11 person. So ID number 11 person has black lines, that's this one. So slope of this line is 0.675, and if you extrapolate this to where age crosses 0, and intercept is 18.95. Okay? And if you look at beta coefficient for ID equal to, and this is the intercept for ID number 2 person. So this is this dark blue. Okay, and then if you extrapolate this line and then intercept, look at where it crosses age of 0, and that intercept is actually 4.75 millimeter lower than the intercept for ID number 11. Okay, so that's how you interpret this output. And then by allowing cross product term with age, and we are fitting different slope for different girl. So if you look at ID equal 2 times age, and this is a slope for ID equal to this dark blue, and comparing with this black line, which is ID number 11. So slope of this dark blue is 0.125 more than the slope for this black line, which is slope for ID number 11. Okay, so by doing that, and we can actually model different slopes and different intercept for each patient, and then that's actually model difference between patient and patient individuality, or between patient difference. I use these three words interchangingly. And what we want to look is not really a comparison between two girls, right? And what we want to see is girl as a group and whether the effective age is positive or not, whether gross measurement increased by age or not. So we are interested in population average, so we are not really interested in comparing between two different girls. So this model actually do fit well with data, but it does not really answer our question. And one way to deal with between patient variation is to model correlation among repeated measures. And that's what we learned in a previous video. Okay, so looking at high correlations indicate much variation between patient and less variation within patient. So we actually achieve the goal by modeling correlation. So today we are actually using a different approach. So rather than looking at correlation, and we are looking at the random effect. And the purpose of doing is actually the same. We are trying to introduce between patient variation, okay, patient individuality in the model, so that we can remove between patient variation. Therefore, analysis can focus what happened within patient, which is a focus of repeated measures analysis. Okay, so we already did correlation method. So we were already finished talking about correlation method. So today we are not going to use correlation structure, although we are going to talk about random effect. The purpose is to remove between patient variations from the analysis. And here we are interested in assessing the overall effective age while still taking within patient similarity. One way is to include ID as a variable. So we did that with linear regression. But problem with this approach is we start comparing between girls, which we don't want to do. And also, this model is severely overfitted. So let's say how many parameters you have. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so we have 40 observations divided by 20, and that's 2. And that's too much to include in one model. So somehow we need to find a way we spend less degree of freedoms, okay, less number of parameters, but maximize fit of the model to the data. Okay, again, we want to introduce between patient variation in analysis so that we can focus. By modeling it, and we can remove that effect so that we can focus what happened within the patient. All right. So I'm introducing 3 different approaches to model between patient variation without spending too many parameters. Okay, and this is actual data. Okay, so for each girl, and we are fitting straight slope. Okay, so this is a slope for this girl, and then we have 10 different slopes. Okay, and we want to simplify this so that we can capture between patient variation and without modeling too many parameters. So that's the goal. So how about this model? And what we do is we are introducing different intercept for different patients while keeping a slope is the same for all patients. And then instead of directly modeling difference between each patient, so the fixed effect model, we compare difference in slope between two patients, two girls, okay? But here, instead of using intercept as a fixed, instead of modeling individual intercept differently, what we are doing here is we are assuming these intercepts are randomly distributed around some mean value, okay, and with a standard deviation of some standard deviation, okay. And so we are estimating only mean and standard deviation, and then tell model and consider these intercepts are randomly distributed around this normal distribution. So we only estimate two parameters, and while we introduce variation among intercept for different patients, different girls. Okay, I keep saying patient, right? And the next one is random slopes and fixed intercept. And what this does is, it allows only one intercept, okay, for entire cohort of 10 girls, but it allows random slopes. So you see this slope is slightly different from this slope, and these are all the slopes are slightly different. So we are telling SPSS to consider these slopes are randomly distributed from normal distribution where mean and standard deviation is estimated from data, okay? And so this again span two parameters. And then while, okay, and it said fixed intercept, so we allow only one intercept. So if you extrapolate this to 0, okay, and you will see sort of all these slopes shared one same intercept. I think I probably have to extend this even further, and so that you can see these all converge to 1 point where the age is 0. Alright, so the last one is random intercept and slopes. Okay? And this model tell SPSS and consider slopes are randomly distributed from normal distribution of mean and standard deviation estimated based on data, and then also intercept are randomly distributed from normal distribution of some mean and standard deviation estimated based on this data. So how many parameters we need to estimate? 4 parameters. And then SPSS will select which structure will best fit the data while not estimating too many parameters. Okay, so that's what we are going to do. So let me read what I have written here. Random effect models allow different intercept or in slopes. So we have random intercept or random slope or random slopes and intercept for each patient by assuming that those intercept or and slopes are randomly distributed from a normal distribution with estimate mean and standard deviation of the set of intercept in slopes, and that the model estimate only few parameters, mean and ST, for intercept or slopes, and yet it is able to allow to model between patient variation, i.e. individuality. This is more efficient than fitting a different line per patient, that it preserves statistical power and through using random intercept in or slopes. So finally, let's begin to fit random effect model using mixed effect model. By the way, the word mixed is coming from effect are mixed from fixed effect and random effect. So model is capable enough to fit two different kind of effect, fixed and random effect. That's where word mixed come from.